This is Lesson 6 in our Calculus 2 series, Exponential Growth and Decay. In this lesson, we see how exponential functions are used to model some real-world problems. And we start by defining a differential equation. A differential equation, or diffeq, is an equation involving a function, say y, and its derivative, or its derivatives. For example, y double prime minus 2y prime plus y equals sine x is a differential equation. Also, xy prime minus y squared equals e to the 2x plus 3 is also a differential equation. A solution to a differential equation is a function y equals f of x that makes the differential equation true, or we say that satisfies the differential equation. So if we find a function for which we could plug y prime here and y here, and this equation is true, we have found a solution to this differential equation. One of the simplest differential equations is y prime equals y, and I claim that you already know a solution to this differential equation. This is saying the function's derivative is equal to the original function. We know that y equals e to the x is a solution to this differential equation because y prime is also equal to e to the x, and e to the x is equal to y. So y prime equals y, and this differential equation is satisfied. But notice y equals 2e to the x is also a solution to the same differential equation, because y prime here is also 2e to the x. That's the same as our original function, so y prime is equal to y, and the differential equation is satisfied. In fact, y equals ce to the x, for any constant c, is the general solution to this differential equation. It's a family of solutions, because y prime is equal to ce to the x, which is equal to y. Now notice, what about y equals e to the x plus 2? Is this also a solution? Well, y prime is equal to e to the x plus 2, and then by the chain rule we multiply by the derivative of x plus 2, which is 1. So our derivative is equal to e to the x plus 2, which is equal to the original function. So yes, this is also a solution to the differential equation y prime equals y. But notice y equals e to the x plus 2 can be written as y equals e to the x times e squared, and e squared can be considered our constant c. So actually this solution is part of the y equals ce to the x family. Now let's take a look at y prime equals ky, for k a constant not equal to 0. For example, y prime equals 5y. I claim that you know the solution to equations of this form. So take a couple minutes and think about what function might solve this differential equation. Please pause the video and work on that. Looking at our example, y prime equals 5y, we're looking for a function that when we take its derivative, the original function gets multiplied by a factor of 5. Well, y equals e to the 5x is a solution for this differential equation. When we take the derivative here, we get y prime is equal to 5e to the 5x. So that's 5y. And so that's a solution to the differential equation. So in general, we have y prime equals ky, y equals e to the kx is a solution of the differential equation because y prime is equal to k e to the kx, or k times y. So this is one solution for this differential equation, just as we have one solution for this differential equation. But what would the family of solutions look like for these differential equations? We can multiply this function by a constant c and still get a solution for the differential equation. So y equals c e to the kx is the general solution to the differential equation y prime equals ky. And let's just check that any equation of this form is a solution. When we take our derivative, the constant multiple of c just carries to the derivative, and when we take the derivative of e to the kx, we get a multiple of k that comes out, so we're here. If we just reorder the multiplication of our constants, we realize that this is k times y. So in fact, this function does satisfy the differential equation. This differential equation, y prime equals ky, is a common model for real-world problems. And it's actually the only differential equation we'll be using in this lesson. So let's take a look at what y prime equals ky is saying. It's saying that the rate of change of the amount y is proportional to the current amount. The rate of change of the amount is proportional to the current amount. So this occurs in population growth and also in the decay of radioactive elements. With population growth, the rate of change of population is proportional to the current population. With the decay of radioactive elements, the rate of change of the amount of an element is proportional to the current amount present. Then in either of these cases, since y prime is equal to ky, we know the form of the solution function. We know that it must be of the form y equals c e to the kx. Or if we use, instead of x, we use t for time, y equals c e to the kt. We know that the solution for this equation must be of this form. And we call k the relative growth or decay rate. So let's take a look at an example. A cell of the bacteria E. coli divides into 2 cells every 20 minutes. A culture of this bacteria starts with 60 cells. So this is bacteria population, so instead of y, I'm going to use p for population. So we know that it follows this model, the y prime equals ky model, so this is p prime equals kp. And we know then the solution of our differential equation is going to be of this form. So it's going to be of the form p equals c e to the kt. So we already know that our population function to model this bacteria population is going to be of this form. Now for this to be a useful function though, we need to figure out what the constants c and k are, because we want to be able to plug in a time t and find the population at that time, find the number of bacteria cells at that time. So let's see what information we're given and if we can find c and k. First thing I want you to notice is that at time equals 0, t equals 0, what do we have here? If we let t equal 0, this exponent becomes 0, e to the 0 is 1. This reduces to p is equal to c. So actually this constant c we can call p0 the initial population. So instead of writing c, let's write p0. p equals p0 e to the kt. And we're given that the bacteria culture starts with 60 cells. So that is our p0. So far we have p equals 60 e to the kt. Let's see what other information we're given and if we can find k. We're told that each cell divides into 2 cells every 20 minutes. Now I'm going to change this 20 minutes to 1/3 of an hour only because you'll see below that parts B through D of this problem ask for things in terms of hours. So because of that, I want to make everything in terms of hours. Now if each cell divides into 2 cells every 20 minutes or every 1/3 of an hour, that means when t is equal to 1/3 of an hour, the number of cells we have is going to double from the original. So we're going to have 120 cells when the time is 1/3 of an hour. Now we can solve for k. We first simplify by dividing both sides by 60, and then we'll take the natural log of both sides. So we get ln 2 is equal to ln of e to the 1/3 k, which simplifies to 1/3 k. Multiply both sides by 3, and now we have k. K is equal to 3 ln 2, or if we want to use a law of logarithms, we can bring this up and make this ln of 8. K is equal to ln 8, and that is the relative growth rate. So now we can put that k value back into our equation for p, the population, and we're here. P is equal to 60 e to the ln 8t Now notice we could regroup and simplify here. E to the ln 8 is 8, so this becomes 60 times 8 to the t. So anytime you can make this kind of simplification with e to the ln of something and simplify, I'm going to expect you to do that for full credit. Also, I just want to point out, keep in mind that this number, 8, is being taken to the t power. 60 is not taken to the t power, so we cannot combine the 60 and the 8. It must stay like this. So now we have a formula. At any time t in hours, we'll be able to find the population of bacteria, the number of bacteria cells. So part A of this question says, find the relative growth rate. Well, we know the relative growth rate refers to K, and we found K to be ln 8. So ln 8 is the answer to part A. Part B says, find an expression for the number of cells after t hours. And that's exactly what we solved here. We found P equals 60 times 8 to the t. So we answered part B. Part C, find the number of cells after 6 hours. Well, all we need to do is plug 6 in for t here. Now, since you're not going to have a calculator on your exam, you're going to leave this as 60 times 8 to the 6th. Part D says, find the rate of growth after 6 hours. Remember, rate of change is derivative, so rate of growth is going to be P prime here. They're asking for P prime after 6 hours. Well, what do we know about P prime? We know that P prime is equal to KP. K is equal to ln 8. P after 6 hours is what we found in part C, that's here. So that's 60 times 8 to the 6th. So P prime, our rate of growth, is equal to ln 8 times 60 times 8 to the 6th cells per hour. And part E, when will the population reach 20,000 cells? Whenever they're saying when, they're asking us to find a time. So they're saying find a time such that the population is 20,000. So we set P equal to 20,000 and we solve for T. First thing we're going to do is divide by 60. So we get 1,000 over 3 is equal to 8 to the t. And now, even though we have an exponential function with base 8, it's not common practice to use logarithms of base 8. We usually use the natural logarithm, or maybe log base 10. So generally with these problems, though, you'll see the natural logarithm everywhere. So we'll take the natural log of both sides here. And when we do that, that allows the t to come down in front here. Dividing out by ln 8, this is our expression for time in hours, which turns out to be approximately 2.8 hours, or 2 hours and 48 minutes. So in this problem, we said that K was the relative growth rate, and I want to point out that that happens when K is a positive value. If K is a negative value, then we're talking about an exponential decay function and the relative decay rate. We'll take a look at a decay problem next. But first, a couple of definitions. Half-life is the time it takes for an amount to be reduced by 1/2. And doubling time is the time it takes for an amount to double. So for example, you have an 800 milligram sample of radioactive element X, which has a half-life of 5 days. So what does that mean? That means it takes 5 days for your sample to be reduced by half. So in this case, when time is equal to 5 days, our sample will become 400 milligrams. They're asking us to find a formula for the mass remaining after t days. They want the mass remaining after 30 days. They want to know when the mass is reduced to 1 milligram, and they want us to sketch the graph of the mass function we found in part A. So parts A through C are very similar to what we did with the bacteria problem, but instead of exponential growth, we have exponential decay. The mass is going to be getting smaller as time goes on. So take a few minutes, please pause the video, start with the same formula that we were using, y equals c e to the k t, and work on the solutions to this problem. So we know our solution must be of the form y equals c e to the k t. Instead of c, I'm using y naught because we saw that that constant c represented the initial population or the initial amount. So I'm going to use y naught and remind myself that this is the initial amount. And we're given that we're starting with 800 milligrams, so y naught is 800. So now our equation looks like this. And again, for this to be a useful equation for us, we need to find k, the relative decay rate. Well, we know that after 5 days, our amount is going to be reduced by half. So when time is equal to 5, our 800 milligrams has become only 400 milligrams. So now, with this equation, we can solve for k. We divide both sides by 800, and then take the natural log of both sides. So now we have k is equal to ln of 1/2 over 5. We know that this is an exponential decay problem, so k should be negative. Now just because you don't see a negative sign here doesn't mean that this value is not negative. In fact, ln of 1/2 is a negative value, so this is a negative k value. So don't be confused by that. Now this k value goes back into our equation. And notice instead of having ln of 1/2 over 5, I've written this as ln of 1/2 times 1/5. And I'm doing that so I can regroup and simplify my e to the ln of 1/2 as 1/2. And then we have 1/5 times t over 5. So our equation here looks like y equals 800 times 1/2 to the t over 5. Part B said find the mass remaining after 30 days. So we need to plug in t equals 30. So we do that. We get 30 over 5 as our exponent. That's 6. And actually this is something that is reasonable to compute by hand. 1/2 to the 6th power is 1 over 64. So we have 800 over 64, which reduces to 25 over 2. So that's 12.5 milligrams. That's the mass remaining after 30 days. And part C asks when the mass is reduced to 1 milligram. So that's find the time for which the mass is equal to 1 milligram. So we set y equal to 1 here, and we find the corresponding t. So we need to solve for t here. We divide by 800, then apply natural logs, and then solve for t. So we're here. But notice we have ln of 1 over 800 and ln of 1/2 in here. We could simplify this a bit. 1 over 800 is 800 to the negative 1, and 1/2 is 2 to the negative 1. So in each of these logarithms, we could take out these negative signs in front, and they'll cancel each other. So this is the same as 5 ln of 800 over ln 2. And that's approximately 48 days. In part D, they asked us to graph our function for the mass of this radioactive element. Now I want you to remember the form of our exponential graphs. Whenever we have a base that is bigger than 1, we have exponentially increasing functions. Whenever we have a base that is smaller than 1, we have exponentially decreasing functions. Now we know that this is an exponential decay function, so we are expecting that it's going to be decreasing. And also we can see that based on our function y equals 800 times 1/2 to the t over 5. So essentially, our base of our exponential function is 1/2 to the 1/5 power. In any case, that base is less than 1, and so we do have a decreasing exponential function. Now, we know that because of this factor of 800, when time is equal to 0, we have 800 milligrams. When time is equal to 0, we have 800 milligrams. So we know this graph goes to the point 0, 800. We also know that it doesn't make sense to talk about this graph for t values that are negative, because we're starting with 800 milligrams and time is moving forward. So it doesn't make any sense to have any part of the graph back here. We're going to start our graph at 0, 800. And then we do have a couple of other pieces of information. We know that after 30 days, the mass is 12.5 milligrams. So after 30 days, the mass is 12.5 milligrams, and after 48 days, approximately, the mass is 1 milligram. So that's here. And so this is a sketch of our function for mass. Now let's take a look at Newton's law of cooling. We're going to let capital T be the temperature of the object, T sub s be the surrounding air temperature, and little t be time. So it's important to keep this notation straight. Newton's law of cooling says that the rate of change of temperature with respect to time is proportional to the difference between the temperature of the object and the surrounding air temperature. Now notice this fits in to the y prime equals ky format, because if we let y equal t minus ts, notice ts is a constant, then y prime is the derivative with respect to t of t minus ts, so that's just the derivative with respect to t of capital T. This is y prime, that's here. So this does fit into the y prime equal ky form. So that means we know our solution is going to have the form y equals c e to the kt. Y, we said, was t minus ts, so that goes here. And so now we have our solution function for the temperature of the object after time t. We're given ts as a constant, and again we're going to have to find our constants k and c in order for this to be a useful function for us. Now one thing I want to point out here is that c is no longer an initial value, because when time is equal to 0, when little t is equal to 0, this is all 1, and we get capital T is equal to c plus ts. So actually our initial temperature is going to be c plus ts. So let's take a look at an example. A thermometer is taken from a warm room of 20 degrees Celsius to a cold room 5 degrees Celsius. After 1 minute, the thermometer reads 12 degrees Celsius. Okay, now before they even ask us for anything, let's see what we can find out about this temperature function. We know that the initial temperature of the thermometer is 20 degrees Celsius. T of 0 is equal to 20. That's going to be c plus ts. We also know that the surrounding temperature, T sub s, is equal to 5, because the cold room has temperature 5 degrees Celsius, and that's the surrounding air that's affecting the temperature on the thermometer. They also tell us that after 1 minute, the thermometer reads 12 degrees Celsius. So when little t is equal to 1, capital T is equal to 12. So let's see how we can use this information to find our formula for temperature as a function of time. We know that we have T equals c e to the kt plus ts. We know that our initial temperature is equal to 20 and the surrounding temperature is equal to 5. So the 5 goes here for ts. When little t is equal to 0 for time 0, we know that our temperature is 20 degrees. So that tells us that 20 is equal to c plus 5, and c is equal to 15 here. So let's take that c and plug it back into our temperature function, along with t sub s being 5. So now we're here, and all we need is k in order to find the temperature function. Well, we know that after 1 minute, the temperature on the thermometer is 12 degrees, so when little t is equal to 1, capital T is equal to 12. When little t is equal to 1, capital T is equal to 12, and so we're here. Now we can simplify and solve for k. We divide both sides by 15, take the natural log, and we get k is equal to ln of 7 over 15. Now let's plug this back in to our temperature function and simplify. E to the ln of 7 over 15 reduces to 7 over 15. So we get t is equal to 15 times 7 over 15 to the t plus 5. And I want to stress again that only the 7/15 is being taken to the t power. This 15 is not. So we cannot combine these two numbers. Now part A of this question says, what temperature will the thermometer read after 1 more minute? So 1 more minute would be little t equals 2. So we plug little t equals 2 here, and we simplify, and that's approximately 8 degrees Celsius. Part B says, when will the thermometer read 6 degrees Celsius? Again, they're asking for a when. That means find the time. So find little t such that t equals 6 degrees. So we have a 6 over here, and we want to solve for t. So we subtract 5 from both sides, divide by 15, and then use natural logs. And so t is equal to ln of 1/15 over ln of 7/15, which is approximately 3.6 minutes. And with this, we'll conclude our lesson on exponential growth and decay.